Imagine you have a disorganized list of 1 million people, and you need to find one single name. If those names are arranged in a massive single-file line, a computer has to check them one by one. If the person you're looking for happens to be at the very end, that takes 1 million separate steps. But modern databases can find that exact same name in just 20 steps. To do that, they have to snap out of that straight line. High-performance software relies on changing how data is organized, shifting away from straight lines into these branching trees. This diagram shows a standard corporate organizational chart. It's the perfect way to picture how a nonlinear data structure works. At the very top, you have the root. In our company, this is the CEO. And yes, in computer science, trees grow upside down from the root at the top. Flowing downward from the root are the branches. These are your middle managers. They act as connection pathways, directing you to deeper, more specific levels of the organization. Finally, at the very bottom, you have the leaves. These are the entry-level interns. They sit at the end of the line, with no subdepartments connected beneath them. If this company were structured like a grocery checkout line, you'd have to ask every single employee down the line to find a specific intern. But with a hierarchy, you go to the CEO, ask for the right department manager, and skip thousands of irrelevant people instantly. By organizing information in this branching shape, computers can bypass massive chunks of unnecessary data simply by following the correct chain of command. Let's make this structure a bit more specific by looking at a binary search tree. The word binary simply means the number 2. In this setup, every parent node is strictly limited to having a maximum of 2 children. This diagram shows how we can sort data using a classic guessing game with numbers from 1 to 100. Our tree starts with 50 at the root, right in the middle. If the number you're looking for is smaller than 50, the computer travels down the left branch. In that one move, it completely ignores every number greater than 50. If your number is larger, it goes down the right branch. Because a binary search tree organizes data exactly like this as it's being entered, the hard work of searching turns into a rapid, automated game of elimination. Sometimes you don't need to find a specific item, just what's most important right now. Just think of a hospital emergency room. Patients aren't treated based on who arrived first. They're treated based on who is in the most critical condition. For this, we use a variation called a heap. In a max heap, there is one rule. The item with the highest priority is continuously pushed to the very top root position. You can also flip the rules to create a min heap. In this setup, the smallest or lowest value bubbles all the way up and stays pinned right at the top. While our binary search trees are designed to hunt down a specific number, heaps guarantee a system always has zero delay access to the single most urgent piece of data. Let's return to searching 1 million items. A binary search tree slices the pile down the middle. That single step instantly eliminates 500,000 possibilities. Then it halves again to 250,000, then 125,000. In just 20 steps, you've found the exact item. This efficiency comes from a mathematical effect where doubling the amount of data only adds one extra step to the search. It's a way to cut the remaining work in half at every single step, preventing the workload from spiraling out of control as data grows. Here is where the scaling gets incredible. If that database grows from 1 million people to 1 billion, which is 1,000 times larger, you don't need 1,000 times more steps. 10 rounds of halving reduces 1,000 down to 1 person. So searching 1 billion names only takes 10 extra steps, 30 total. This reduction in effort is the mathematical superpower that allows modern global tech platforms to handle billions of users every second without crashing. So to review, trees organize information into hierarchies. Binary search trees use that hierarchy to play an incredibly fast game of elimination, and heaps guarantee that the most important data is always first in line. If this helped you picture how your data actually works, hit the like button and subscribe. Let us know in the comments which computer science topic we should decode next. Learning data structures is a fundamental upgrade to how you solve complex problems. Mastering the shape of your data is the first step to mastering the logic of the digital world.